Welcome back viewers. Welcome to this course. Today we are going to start with the lecture 23. So, in the previous lecture we have discussed that LU decomposition methods using the Gauss elimination and the Kraut's method. So, today we will go further. So, in the previous lecture we have discussed one example. In that case we was able to find the LU decomposition using Kraut's method. So, today I will take another example. So, let us take a matrix A and suppose this matrix is given as 1, 2, 6, 4, 8, minus 1 and minus 2, 3, 5, and I want to reduce it to the LU decomposition. So, in this case I will take my L. So, I will put this equal to 1, 1, 1, L 2 1, L 3 1, L 3 2 into U 1 1, U 1 2, U 1 3 and U 2 2, U 3 3 and U 2 3. Now, I know that from here I can say that my U 1 1 is 1, U 1 2 is 2 and U 1 3 is 6. So, that is from step 1. Now, from step 2, if I take the using the second row, I will get L 2 1 U 1 1 is equal to 4, and from here I will get the value of L 2 1. So, L 2 1 is giving me 4 by U 1 1. So, it is 4. Now, the next step will be to finding U 2 2. So, I will find out L 2 1 U 1 2 plus U 2 2. So, that should be equal to 8. So, from here my U 2 2 will be 8 minus L 2 1 U 2 2. So, it is 8 minus L 2 1 is 4 and U 2 2 is 2. So, it is 4 into 2 8. So, that is the value 0. So, in this case what is happening? The value is coming 0, and if you remember that in the next steps to find the value of other elements, some places we have to divide by U 2 2, but U 2 2 is coming 0. So, in this case we cannot divide by U 2 2. So, from here I can say that LU decomposition is not possible. And if you look from the matrix A, then you can see that it is not diagonally dominant. So, in this case my matrix A is not diagonally dominant. So, it may happen that if I change this one and make this matrix as a diagonal dominant, then if I do the LU decomposition, so in that case it may possible that I will get the LU decomposition. So, that is always there. If a matrix is diagonal dominant, then the LU decomposition is possible. So, from here in the previous method where we have taken LU decomposition. So, I have started with the method 1, LU decomposition using Gauss elimination. So, in the LU decomposition using Gauss elimination, we have ignored interchanging of rows. So, in that case we have ignored the interchanging of rows. So, based on this one So, in the previous one LU decomposition not possible using the Kraut's method. So, that is it. Now, we want to find out the another method. So, I am just telling you that in the starting we have started with the LU decomposition using Gauss elimination and we have ignored the interchanging row. So, in this case I am going to start with the new method and that is called the reduction of PA is equal to LU decomposition form, where P is a permutation matrix. So, it is a permutation matrix. So, I can write the definition of permutation matrix. So, a matrix n cross n matrix permutation matrix P is a matrix with precisely one entry whose value is 1 in each column and row, and all other values, all other entries are 0. So, that is called the permutation matrix. For example, if I define the P as, suppose I take a matrix 0 0 1 0 1 0 0 0 0 1 0 0 0 0 0 1, suppose I take this matrix 4 by 4 matrix I have taken. So, that is a permutation matrix. In each row and each column only one element. So, if I want to this one so this is a permutation matrix. So, in the permutation matrix what we have done, we have started with the I, that is the identity matrix, zero 0 1 0 and 0 0 0 1, and then we have interchanged the first row. So, this is this permutation matrix, if I save, I can save it as 3 1 2 4. So, it means I have interchanged the third row with the first row, then this row with the second row and the second row with the fourth row. So, fourth row is at the same place. So, that is my interchanging of the rows. So, this is, it gives you only the interchanging row, because we know that if I want to make the matrix a diagonal dominant, then I have to change the interchange the rows. So, that we have also seen at the Gauss elimination method. To make the matrix diagonal dominant, we have done the partial pivoting, and the partial pivoting was, what was that? That was just to interchange the rows, so that I can bring the highest element at this location and this location, this location and this location, not in the permutation matrix, but in the given matrix A. So, in this case what we are doing, now from here I can say that I have a matrix A. Now, I am applying permutation to this and then I am doing the LU decomposition. So, that is called the LU decomposition method. So, what I am doing now, suppose I have a matrix A, suppose I take 3 by 3 matrix. So, I will take A, then suppose I take a identity matrix I with the interchanging of first and third row. So, that I know that if I pre-multiply, the same will happen in the A. Then I am applying L1. Then suppose I am doing L2 maybe, so I should take, so I can take suppose 2 3, then I am taking L2. So, this is my L2 and then after that I am getting my U. So, from here I can say that my A will be what? L2 I23 L1 I13 inverse U. So, that is my A, and I know that this I determinant is 1, I inverse is also I. So, this type of matrices are called involutory matrices. So, from here, if you see from here, I can write this matrix as I13 inverse, L1 inverse, I23 inverse, L2 inverse U, and that is my A. So, from here I can write, now I can write this as a I13 I23. So, I will putting the value here. So, I will getting I13 23. So, this is I am multiplying by this one, I13 inverse L13, I23 inverse L2 inverse, and then L13. So, this is I am getting U. Now, from here this is my I. So, that will become my PA, and if you open this one, just do the calculation, then it will give you PA is equal to LU. So, that is my L and this is my U. So, this will give me the lower triangular matrix and this will give me the upper triangular, and my PA will be this one. So, that is the matrix with the partial probability, with the permutation of the rows. So, this is we have to do when we come across the ways, as we have done the example for the Kraut's methods. Because in the example of the Kraut methods, if I change this matrix into in this form, suppose I write 4 8 minus 1 and then 1 2 6 here and then minus 2 3 5. So, in this case my A11 will be 4, U12 will be 2, U13 will be 6, and then my L21 U11 will be 1. So, from here I can say my L21 will be 1 by 4, and then if I want to find my L21, so my so this one I want to do. So, my U22 will be 8, no not 8, it will be 2. So, that will be equal to 2 minus L21 into U22. So, what is the L21 is 1 by 4 into U22. U22 is, it is U12, yeah, U12, right. So, it is equal to U12, that is 2. So, 2 minus, so it is 2 minus 1 by 4 into U12, 2. So, that will be 2 minus half. So, it is 3 by 2. So, now it is becoming non-zero. So, if I do this one, then it may possible that we will get the matrix, it not may possible, it will, you will get the Kraut's methods for this one. So, now after doing this one, so all this will make the Matlab code later on for Kraut's methods, for PA, LU decomposition. Now, we take the another very important method, and that is called the Cholesky method. So, what is going to happen in the Cholesky method? So, if I take a matrix A n by n matrix, and this matrix is symmetric and positive definite. So, two conditions are there, symmetric and positive definite, then the LU decomposition is given by Cholesky. So, in this case, if I take the matrix A symmetric, it means A is equal to A transpose, and then what will happen? I have my LU decomposition. So, I will take A transpose, then it will be LU transpose, and in this case it will be U transpose L transpose, and my A transpose is equal to A. So, it means that should be equal to LU. So, from here I can say that either UT is equal to L or LT is equal to U. So, from here I can say that my matrix A can be decomposed as L, then U is L transform or U transform U. So, in this case what is going to happen? Now, suppose my L is, so suppose I take this method, this notation. So, let my, this is L11, L22, LNN. So, L12, L21, LN1, this one. So, now my L transformation will be the same element, but it will become the upper triangular matrix. So, from here I can say that I need to find only these elements, and what, how many elements are there? So, we have n elements at the diagonals plus n minus 1 at these points plus n minus 2 and so on up to 1. So, this will be equal to the n plus 1 by 2. So, now I have to find n into n plus 1 by 2 elements from this, because in the matrix we have n square elements. So, instead of n square elements we need to find only these elements. So, we have to find out much number of elements, and based on this L, then I can find my L transpose, and then I reduce my A into the L transpose notation. So, this method is only for the symmetric matrix and the positive definite matrix. So, let us have some discussion about positive matrix and the symmetric matrix. Now, why we need the symmetric matrix? So, we know symmetric matrix. So, suppose A is n cross n matrix, so it is called the symmetric matrix if A transpose is equal to A. So, when I talk about the symmetric matrix, I assume that A is a real matrix. So, with the benefit of the symmetric matrix is that it has all eigenvalues real, because when we have the real eigenvalues, then we can say that whether it has a positive sign or negative sign. So, the benefit with the symmetric matrix is that it has all the eigenvalues that is real, and this we can also prove. I know that for the eigenvalues I can write my Ax is equal to lambda x, where lambda may be complex because I do not know. I have to prove that it is a real or complex. So, if it is a complex, A is real and this is the complex, so x is also complex. Now, what I do is that I take conjugate. So, this is equation number 1, apply conjugate and then transpose. So, I can take conjugate. So, A is a real, so does not matter. Lambda is a scalar, so I will put the conjugate and then this and then I take the transpose, because lambda is a scalar, so transpose is nothing, so I will get the same value. So, from here I can write this equation as x transpose A transpose is equal to, so this one I have written. Now, from here I know that A transpose is equal to A. So, that gives me, because, so that gives me A is equal to lambda. So, that equation I write as 2. Now, what I do is that I am take the dot product, taking dot product of equation 1 with x bar transpose. So, what I will get? I will get x bar transpose A x is equal to x bar transpose lambda x, and lambda is a scalar. So, I can take this as a outside and this will be this one. Now, same thing I am going to do with taking dot product of equation 2 with x. So, I will take with x only of the equation number 2. So, from here I can write x transpose A x is equal to lambda x. So, that is the dot product I have taken 3 and 4. So, from equation number 3 and 4, because this is just a vector, so I can take the transpose. So, from 3 and 4 you will see that this and these are same. So, from here I can write that lambda bar x transpose x, this value is same as lambda x transpose x. And what is this? So, this is just a, because if suppose x is a vector x1, x2, xn and is a complex valued. So, x bar transpose will be x1 xn conjugate and then multiply by x. So, suppose I am doing this one. So, x transpose x will become this into x1, x2, xn. And I know that x1 bar with x, the complex number multiplied by its conjugate will give you the modulus value, because I know that a plus ib multiplied by a minus ib is equal to a square plus b square, and the a plus ib modulus is a square plus b square under the root. So, this is the modulus square, I can say that. So, if based on this one, if you see from here, then this quantity is basically I can write from here that this is first, then second one, then third one. So, square is equal to lambda square. So, this one I can write, because from here I will get x 1 bar square plus x 2 bar square and x n modulus value square. So, this I take as a norm. So, this value will be there. So, from here I can eliminate this, and from here I will get this equal to this. So, from here I can say that lambda is always real. So, for the symmetric matrix, the eigenvalues are always real. After that, I will define the term positive definite. Positive definite, and that matrix is already symmetric. Positive definite symmetric matrices, because the matrix A is already symmetric and I am discussing the positive definite. So, in this case, from here I know that A x is equal to lambda x. Now, and positive definite means that a matrix A, that is n cross n, is said to be positive definite if all eigenvalues are greater than 0, and it is called semi positive definite. This is for all I. Lambda I is greater than or equal to 0 for all I. So, it means that my all the eigenvalue should be greater than or equal to 0. So, if it is a positive definite, it is strictly greater than 0, otherwise greater than or equal to 0. So, from here I know that how to find the eigenvalue. I can find the eigenvalue as a Ax is equal to lambda x, where x is not equal to 0 and lambda is my eigenvalue. I can multiply this with the A transpose, and I can write this one as. So, from here I can write x transpose x, and from here I can write my lambda is equal to x transpose Ax is equal to x transpose x. So, x transpose x is the square. So, from here this quantity I can be written as square. So, from here this quantity is always positive. Suppose this is positive. So, if x transpose Ax is positive for all x, then my lambda is always positive, and then we will say that the A is positive definite. So, in that case I will say that A is positive definite. Other way is to find that how we can find out that A is positive definite. So, then we can say that all the pivots are positive. So, all the pivots will be positive. So, what are the pivots? Like I have a matrix A, and suppose I take the matrix maybe 3, 2, 1, 1. So, this is a symmetric matrix, A transpose equal to A. Now, in this case, what are the pivots? So, the first pivot is 3. So, and the next pivot is, so the first pivot 3, and the next is, so next is I will call it, I can reduce this with the Gauss elimination, or the another method is that finding the determinant. So, it is a 6 minus 1, that is 5 divided by 3. So, that is 5 by 3. So, in this case 3, so in this case my pivot 3 is positive, 5 by 3 is positive. So, from here I can say that this is positive definite. So, this matrix is positive definite matrix, and from here I can give one information that what are the pivots, how we can find the pivots. So, pivots can be find out with the the determinant, because we consider the leftmost square matrices. So, in that case we will get the determinant A, the determinant of this one divided by A k minus 1 k minus 1, where A k means where A is the leftmost k cross k submatrix, and this is the previous one. So, like this is a 2 cross 2 matrix and this is the previous one. So, I have done taking the determinant of this divided by this. So, that is a pivot. So, based on the elements of the pivots, because it is very easy to reduce this matrix into the Gauss elimination type, and then we can find the pivots. So, based on the sign of the pivots, I can say that whether my matrix is a positive definite or not. So, from here I can say that sign of pivots is same as sign of eigenvalues. So, based on the sign of the pivots, I can find out that whether the matrix is positive definite or the negative definite or the mixed type. So, that is all about the positive definite matrix. So, we will stop today here. So, in the today class, we have discussed about that how we can apply the permuted matrix LU decomposition method, and then we have discussed another method, that is Cholesky method for symmetric matrix and the positive definite matrix, and the next class will discuss about the other method also. So, thanks for watching, thanks very much.